You can go ahead, Roberto. So Roberto will present his work on this direct displacement-based seismic design of non-structural elements.
Okay, so I am Roberto Merino, and the title of my thesis is Direct Displacement-Based Seismic Design of Non-Structural Elements. My advisors were André Filatro and Daniele Perron. So first, what is the importance of non-structural elements in seismic performance of buildings? There are three main reasons. The first is that non-structural elements represent a major source of investment in buildings, and therefore they can contribute to significant economic losses during earthquakes. The second is that damage to non-structural elements can produce a loss of functionality in a building, even if the structure is undamaged. And this is especially important in critical facilities like hospitals or airports. The third is that non-structural elements can fall or break and cause life safety hazards to building occupants. So because of this, current seismic design guidelines usually provide a force-based seismic design procedure to ensure that the non-structural elements will achieve a certain performance during an earthquake. All of these procedures follow the similar basic principles. I will use them as an example here, Eurocode 8. So usually a force-based design procedure for non-structural elements follows the following three steps. You estimate or assume the period of the non-structural element. Then you estimate the equivalent elastic acceleration demand on the non-structural element. Finally, you estimate an equivalent lateral force that the non-structural element should be able to withstand. And this force is usually computed as the product of the effective seismic weight of the non-structural element times the acceleration demand on the non-structural element. This force usually takes into account the behavior factor, which divides the force by the behavior factor, which takes into account the nonlinear behavior of the non-structural element. So what are the problems with this procedure? Well, first, it has an overly simplified definition of the estimation of the acceleration demand on the non-structural element. There are difficulties in estimating the non-structural period. Behavior factors are not scientifically derived. And finally, that non-structural displacements which cause damage to the non-structural element are not considered explicitly in the design procedure, but they are taken into account only implicitly through the behavior factor. So why the displacement-based design for non-structural elements? Well, first, because many non-structural elements are damaged due to excessive displacements relative to the point of support in the structure, which these displacements are generated by inertial forces. And second, for many non-structural elements, stiffness is proportional to strength, and therefore it's difficult to know the period before the design is completed. So how do we apply direct displacement-based design to non-structural elements? So basically we just apply the same basic principles as direct displacement-based design for building and bridge structures proposed by Priestley et al. So the procedure would look something like this, following these steps. So in step one, you can define the target non-structural displacement that you want the non-structural element to achieve. With that, you couple that with a definition of a seismic hazard level. This seismic hazard is defined in terms of a relative displacement flow response spectrum. In step two, you select an appropriate value of equivalent viscous damping to represent the nonlinear behavior of the non-structural element. In step three, you can determine the equivalent non-structural period by entering the relative displacement flow response spectrum at the level of equivalent viscous damping with the target displacement and finding the period. In step four, you can compute an equivalent non-structural lateral stiffness for the non-structural element using the basic relationship between mass, period, and stiffness. And finally, in step five, you can compute the seismic design, an equivalent lateral seismic design force for the non-structural element, which is the product of the equivalent stiffness and the target displacement. So using existing knowledge available in the literature, we performed a preliminary example on how this would look. We used as an example a suspended piping system supported on the top floor of a 5-story reinforced concrete moment resistant frame, which was located in Casino in Italy. So the suspended piping system that we use had a plan view of an L shape with a feed mainline of 18 meters and a cross mainline of 36 meters. The seismic force resisting system of this piping system was made of trapezium restrained installations with braces made of channel elements. So to perform the design, the direct displacement-based design, we assumed we used what was available in the literature to estimate the relative displacement flow response spectrum using a procedure proposed by Calvi, which assumes constant non-structural displacements for periods longer than the fundamental period of the structure. And then for the damping model, we used the results of reverse cyclic tests from a trapezium restrained installation performed by Wood et al. And we used this to develop a simplified, a very simple and ad hoc damping model. So we compared also this preliminary example with the results from Eurocode 8 using, since the force-based design procedure requires an assumption of the period of the non-structural element, we assumed that the ratio of the period of the non-structural element to the fundamental period of the structure was equal to 0. And we compared it to the direct displacement-based design procedure. So for the Eurocode 8, the final design had 3 transversal supports in total throughout the pipeline and 2 longitudinal supports, while for the direct displacement-based design, we had 6 transversal supports and 5 longitudinal supports. So we appraised these designs using nonlinear time history analysis. So we ran nonlinear time history analysis of the supporting frame, and then we recorded the floor accelerations at the top floor, and then we used that to run nonlinear time history analysis of the suspended piping systems. So using 40 ground motions, we followed this process, and then we recorded the peak displacements for in both the transverse trapezies and longitudinal trapezies. And we fitted a log normal distribution to these peak displacements. So now here we compare the results for both the Eurocode 8 and the direct displacement-based design procedure. So in these plots, you can see the log normal distribution of the peak displacements. And then as a black dashed line, we see the target displacements that we assumed at the beginning of the design process. So the perfect result would be to have a probability of occurrence of 50%. In the case of the direct displacement-based design procedure in the transverse direction, which is the one that governs the design, since the target displacement in the transverse direction is lower than in the longitudinal direction, the probability of occurrence of the target displacement is 60%, while for the Eurocode 8 is 0%. So in reality, the assumption in the Eurocode 8 tends to be very unconservative, while direct displacement-based design gives a relatively good result. So the results of this preliminary example were published in a paper in the Journal of Earthquake Engineering. So after this preliminary example, we searched for what were the areas in which this procedure can improve. We identified 2. One was the definition of the relative displacement flow response spectrum, and the other one was the definition of damping models for non-structural elements. So first I will talk about the definition of relative displacement flow response spectra. So we wanted this to be based on a simplified methodology to estimate flow response spectra that avoids running nonlinear time history analysis of the supporting structure using multiple records. And we also wanted that for convenience, the pseudo-spectral relationship to transform absolute acceleration and to relative displacement flow response spectra would apply. So we went to the literature, we found a recent simplified methodology proposed by Sullivan et al. To estimate the absolute acceleration flow response spectra. The main steps of this methodology are as follows. First, in step 1, you perform an eigenvalue analysis of the supporting structure to find the periods and mode shapes. In step 2, you perform a spectral analysis. Step 3, you use those results to compute the contributions to the peak floor accelerations of each floor of each of the modes of the structure. And then you use those values to compute the contributions to the absolute acceleration flow response spectrum of each of the modes. These contributions you can calculate with a simplified method, some empirical formulations, some empirical equations which give a rising branch the flow response spectrum up to the mode period of the supporting structure, and then a decreasing branch for periods longer than the mode period of the supporting structure. And then you combine all these contributions using an SRSS combination, and you get the final estimate of the flow response spectrum. So we compared the results from this simplified methodology by Sullivan et al. With the results from nonlinear time history analysis. We compared the median using the median flow response spectrum from the fourth floor of a four-story reinforced concrete frame located again in Casino, and using 70-year ground motion so that the frame remained completely elastic. We computed the flow response spectra for 5% non-structural damping. So here we compare, in the first plot, we compare the results of the absolute acceleration flow response spectrum. The black curve is the latest version of the Sullivan et al. Methodology. The blue curve is the median from nonlinear time history analysis. So if we apply the pseudospectral relationship to the black curve, we get the result, and we compare it to the median relative displacement flow response spectrum from nonlinear time history analysis. We get these results that we see that for periods longer than the fundamental period of the supporting structure, and as the non-structural period increases, we get increasing non-structural displacements, while the median from nonlinear time history analysis converges to the physically correct peak floor absolute displacement. This quantity is the correct quantity because an infinitely flexible non-structural element will remain completely static as the ground and the structure move below it. So we wanted to propose an equation that will do something like this. And this is the equation we proposed. This equation has as two boundary conditions, the peak of the floor spectrum and the peak floor absolute displacement at infinite period. So this is the equation for this branch, and this equation depends on the peak floor absolute displacement, the mode period of the structure, the non-structural period, and the peak of the absolute acceleration flow response spectrum. So the problem with that equation is that we need an estimate of the absolute displacement flow, the peak floor absolute displacement. This is not a readily available quantity, so we propose an equation to estimate it. We realize that the absolute displacement is the sum through time of the ground displacement and the relative displacement of each floor. These two time histories are not in phase, so we believe that the peak floor absolute displacement can be estimated as the square root of the sum of the squares of the peak ground displacement and the contributions to the relative displacement or the relative displacement of the floor of each of the modes of the structure. So the relative displacement of the floor can be taken from an inelastic range through a model analysis and for the nonlinear range using a nonlinear static method. So we validated this equation. We use 4 buildings in Casino, located in Casino. Because of time constraints and space constraints, I can only show you the results for the 4-story building that I already presented in the example before. In these plots, you can see in the horizontal axis the results from this equation, and in the vertical axis the results from nonlinear time history analysis. The black solid line is the one-to-one relationship between the two, and the black dots are the individual results from different ground motions. So as you can see here, the black dots align relatively well with the black solid line, so that this equation is a good predictor. We conclude that this equation is a good predictor of the peak floor absolute displacement. So using that, we validate our new methodology to estimate flow response spectrum. Here you can see again the validation made for 4 buildings in Casino, but again for space and time constraints, I can only show the results for 2 buildings. These 2 buildings were a 2-story reinforced concrete frame and a 4-story reinforced concrete frame, the same one that I used in the example above. So we did this also in the elastic and in the nonlinear range. Here the results you can see in terms of acceleration displacement format, and also in the small frame here you can also see the results for the relative displacement flow response spectrum. You can see here the black solid line is the result for our simplified methodology, and the black dashed line is the median from nonlinear time history analysis. So you can see that the results match relatively well to the median for both the elastic range and the nonlinear range. In the nonlinear range, we applied some additional considerations, like the capping of the peak floor acceleration of the first mode of the supporting structure, using Newton's second law as the base shear of the effective mass of the building, and then some period elongation in the two first modes of the structure, using the simple equation that the effective period equals the initial period times the square root of the ductility. So the results match relatively well for both cases, the nonlinear and elastic. So some observations and future work on this topic. The proposed methodology provides an effective way to estimate flow response spectra for direct displacement-based design and assessment of non-structural elements. The methodology still requires some validation with a variety of supporting structures with different seismic force resisting systems and with different ground motions. The methodology also requires validation on other locations with a higher seismic hazard that will induce a more pronounced nonlinear response of the structure. And the results of this study have been, the main results of this study have been published in a paper in Earthquake Engineering and Structural Dynamics. So now I will talk about equivalent viscous damping ratio for non-structural elements. So this was initially based on Jacobson's damping model. So this implied taking the results from reverse cyclic tests as the ones you see here, and then integrating each of the loops using, and then applying this equation proposed by Jacobson many years ago, and then plotting the displacements with the equivalent viscous damping ratio. Then we calibrated the results using the results from nonlinear time history analysis of single degree of freedom systems. So we applied this to two typologies of non-structural elements: suspended piping trapezium string installations and pallet type steel storage racks. So first we will see the results for suspended piping trapezium string installations. We use the results from reverse cyclic test performed by Perrone et al. Perrone et al. Tested the transverse channel, longitudinal channel, transverse rod, and longitudinal rod trapezies. So the results of the tests are presented here in the first plot. If we apply Jacobson's damping model, we get the results that you see here in the second plot. We decided that for these types of non-structural element, the best thing was to represent the deformations for the damping model in terms of the drift of the trapezium string installation. This was because it was usually this is done in terms of ductility, and we decided to use drift because it was difficult to define a yield displacement for these systems, and because we assume that the nonlinear deformations of these systems will be concentrated always in the proprietary hinge connections between the elements. So here in these plots, you can see the results of applying Jacobson's damping model for the four systems. The black dots are the results from each of the loops in the experimental results. And then to this, we fitted a damping model that will represent the variation of equivalent viscous damping with the drift. We performed the same procedure for pallet type steel storage racks. We did this both in the down aisle and in the cross aisle directions. But in the down aisle direction, we did this using results from reverse cyclic tests of beam to upright connections and base plate connections. And in the cross aisle, using cross aisle frames, the results were taken from the project Seisracks and Seisracks 2. And because of the time constraints, I will only show the results for the down aisle direction. So since we had only results from beam to upright connections and base plate connections, what we did was fit models to this data, hysteretic models to this data, and then develop numerical models of full-scale pallet type storage racks. And then we perform reverse cyclic analysis to find the hysteretic response, and then we apply Jacobson's damping model, and then we developed a database that relates ductility in the rack with equivalent viscous damping ratio. And then we fitted a model to this data. So because Jacobson's damping model is strictly valid for systems in a resonance steady state under harmonic loads, we applied an iterative procedure that was based on the results of nonlinear time history analysis to calibrate the damping model. This procedure was similar to a procedure that was already done for structural systems, for direct displacement-based design of structural systems. So the procedure more or less goes like this. We select a representative range of the damping model that we want to validate. Then we design single degree of freedom archetypes using each of these target deformations, using the basic principles of direct displacement-based design. Then we run nonlinear time history analysis of these archetypes, and we compare and we record their peak displacement, and then we compare the results between the target displacement that was used for the design and the peak displacement from time history analysis. With this, we can assess the results of the damping model. But if we want to calibrate it, we continue by iterating. If the displacements are not the same, we can change the value of the equivalent viscous damping and repeat the whole process until we get a similar relationship between the target displacement and the displacement from time history analysis. So this process requires nonlinear models of non-structural elements, which were calibrated from reverse cyclic tests. In our case, we use the pinching for material model in OpenSys, and a set of floor motions, which we generated using the FreeMap P695 far field set and single degree of freedom representations of supporting structures. So here I present the results for the trapezius string installations. I just present the results for the channel trapezius since there is no time to present also the results for the rod trapezius. In the first plot here, you can see the relationship between in the horizontal axis, the target drift used for the design, and in the vertical axis, the peak drift from nonlinear time history analysis. The black solid line here is the one-to-one relationship, and the individual results of each analysis are the gray dots. The white stars in the plot represent the median from the gray dots, and they should be the ones that match more or less the one-to-one relationship. So, so I present what you can see here in these results. As in general, the results show that the median tends to be unconservatively high for low drifts and very conservative for higher drifts. So we perform the whole iterative procedure, and we get these new damping models that you can see here, which we fit a new damping model for the trapezius, and then we validate the results again using the same procedure, and we get the results that you can see in the last plot, in which the median now aligns better to the one-to-one relationship. We did the same procedure for the pallet type steel storage racks. Again, we did both for the cross aisle and down aisle directions. Here I just present the results from the down aisle direction. So so we repeat the procedure. In the first plot, we have the target ductility that we use for the design, and in the horizontal axis, and in the vertical axis, the peak ductility obtained from nonlinear time history analysis. The black line is the one-to-one relationship. The gray dots are the individual results, the individual analysis, and the black dots are the median from the gray dots. And as you can see, the results show that in general they are good, but they tend to be a bit unconservative since they are a bit high. So then we follow the whole procedure. We fitted the damping models to the results from the iterative procedure. We fit a damping model, and we get this new model, and then we assess the relationship, and we get a closer relationship to the one-to-one relationship. So the only particularity here is that we use ground motions instead of floor motions, because in general racks are usually installed at the ground level of a building. So some observations and future work on this topic. Jacobsen's damping model performed relatively conservative for suspended piping trapezius string installations for high drifts, and then slightly unconservatively for pallet type steel storage racks in the down aisle direction. The calibrated damping models gave a better estimate of the design deformations for both non-structural systems. The calibrated damping models that we present here still need to be validated using other sets of floor or ground motions and multiple degree of freedom systems for the suspended piping, multiple degree of freedom supporting structure systems for the suspended piping installations. And the procedure developed here is general and it can be applied to any typology of non-structural element, provided that the results from reverse cyclic tests are available. So the results from this study were published in 2 papers in the Journal of Earthquake Engineering. One was related to suspended piping and the other one to pallet type steel storage racks. So finally, we did the appraisal of seismic design methodologies for non-structural elements in Europe. We used a case study suspended piping trapezial strain installation. We appraised the results from Eurocode 8, the Italian code, and the direct displacement-based design procedure using fragility curves for a life safety limit state. And we did the design. We assumed that it was the piping system was installed on a case study suspended on a case study building located in Casino, Italy, and located in the top floor of the building. The seismic force resisting system of this suspended piping system was assumed to have trapezoidal strain installations made of channel braces, and is the same suspended piping system we used for the preliminary example that I presented before. So, because the force-based design procedure again requires an assumption of the period of the non-structural element, we made 2 assumptions for both Eurocode 8 and the Italian code. We assumed that either the period ratio between the period of the non-structural element and the period of the fundamental period of the supporting structure was either 0, which means that the non-structural element is assumed to be completely rigid, or was equal to 1, which means that the non-structural element is in perfect resonance with the supporting structure. So applying these designs, we see that the Eurocode 8 and Italian code give the same, when we assume that the period ratio is equal to 0, give the same final result of 3 transversal supports and 2 longitudinal supports over the whole pipeline. The Italian code with the period ratio equal to 1 gives 5 transversal supports and 3 longitudinal supports over the pipeline. And the direct displacement-based design procedure and the Eurocode 8 design procedure with assuming the period ratio equal to 1 gives 6 transversal and 3 longitudinal trapezies along the pipeline. So we ran a full multi-step analysis of these three archetypes, and we fitted fragility functions to these results. You can see here in the fragility curve for the transverse trapezie and the longitudinal trapezie. In the horizontal axis is the seismic intensity, and in the vertical axis you can see the probability of the peak displacement exceeding the target displacement for the seismic intensity. In these plots you can also see as a black dashed line the design seismic intensity. So again, the transverse trapezies govern the design, and you can see that first the Eurocode 8 and Italian code with the assumption of the period ratio equal to 0 is very conservative with a probability of exceedance of 100%. And then that the direct displacement-based design procedure and the Eurocode 8 design procedure with assuming the period ratio equal to 1 give a probability of exceedance of 65% in the design level earthquake, while the Italian code gives a 90% probability of exceedance with the assumption of the period ratio equal to 1. So with this, we conclude that the direct displacement-based design procedure gives similar results to the existing force-based design procedures now, but it's more complicated with 5 steps instead of 3, but it does not require an unwarranted assumption on the value of the non-structural period or an iterative procedure, and it's more intuitive since the displacements are considered explicitly at the start of the design process. So the innovative aspects of the dissertation were the development for the first time of a direct displacement-based seismic design procedure for non-structural elements, the development of a simplified procedure to estimate consistent flow response spectra, the development of a general procedure to generate damping models for non-structural elements, and the application of this procedure to 2 typologies of non-structural elements, the appraisal of seismic design, and finally the appraisal of seismic design methodologies for non-structural elements using fragility functions. So future work on this will be the extension of the direct displacement-based design procedure to other typologies of non-structural elements, like suspended ceilings, furniture, anchored equipment, vibration isolated equipment, chimneys and parapets, And then finally, the development of a direct displacement-based seismic design procedure for non-structural elements supported by more than one floor of the structure. I would like to acknowledge the Italian Ministry of Education, University and Research, the Youth Center Foundation, and the Italian Department of Civil Protection for their financial support in different ways to this project. Reference and thank you.
Thank you, Roberto, mostly for staying within the 30 minutes, almost.